Let us study bending of a cyclist. Now here a cyclist is moving on the level road. As he negotiates a curve, so we will notice that always the cyclist will bend from the vertical position in which he is. So the cyclist is moving on a horizontal road comfortably. Now he negotiates a curve. You see, he has bent. Which side he has bent? He has bent towards the inner side of the circle. So if the curved path is in this direction, so he has bent towards inner side. If the curved path is like this, he has to bend the other side. Look at the picture again. Now the cyclist is moving straight, horizontally. Now he negotiates the curve. So he bends and comfortably negotiates the curve. Why he bends? He bends because the normal reaction coming from the ground, the component of that can provide the necessary centripetal force so that he can easily negotiate the curve. Let us see this picture again. Here I will draw the position of the cyclist in two cases. When he is moving flat on the horizontal road, the position of the cyclist will be vertical. This is the horizontal road. The position of cyclist is vertical. But as he starts negotiating a curve, now the curve is towards right. Then what do you notice? Instead of cyclist being vertical, this position, the cyclist bends. Now the cyclist will be in this position. With vertical, he has bent by an angle theta. By bending, what he does, let us look into the forces, component of forces which are acting on it. When he is vertically on a horizontal road, the weight of the cyclist as well as the person, the bicycle and the cyclist, mg is in vertically downward direction. Normal reaction also will be in this direction. So the normal reaction mg component are balanced, so he can move comfortably without taking a bend, moving in a straight direction. But as he wants to negotiate a curve toward this side, he has to generate a centripetal force here. So now what happens? Mg or the weight of the body acts again in the downward direction. This is the direction of mg. But normal reaction he is getting from the ground. So the normal reaction will be now in this direction. This is r. This normal reaction, this angle theta. So we can split this normal reaction into two components. Since this angle is theta, this component will be written as r cos theta. This component is r sin theta. Now r sin theta, the component is toward the center of the circle. Therefore, if it provides the necessary centripetal force mv square by r, the bicyclist can negotiate the curve comfortably without skidding. So cyclist provide himself the necessary centripetal force by leaning inwards on a horizontal track while going around a curve. Consider a cyclist of weight mg, we have considered here, taking a turn of radius r with a velocity v. In order to provide the centripetal force, the cyclist leans through an angle theta, as I have shown you in this figure. Weight mg acts vertically down at the center of gravity of the cyclist, and the normal reaction comes from the ground, will act along the line making an angle theta with the vertical. The vertical component of r is r cos theta, and for the normal reaction which you take it, which is balancing the weight of the cyclist. While the horizontal component r sin theta will provide the necessary centripetal force. So from the figure we get r cos theta component is balanced by the weight component. Weight W is equal to mg. Equation 1. R sin theta component should provide the necessary centripetal force mv square by r. This is equation number 2. Now dividing 2 by 1. What do you get? R sin theta by r cos theta is equal to mv square by r divided by mg. Or we can write simply tan theta is equal to v square by rg. The cyclist should bend through an angle theta, and that theta will be equal to tan inverse v square by rg. If the cyclist bends by this angle theta, this r sin theta component can provide the necessary centripetal force and the cyclist can negotiate a curve without skidding. See, the cyclist is moving in a horizontal path. Now as he comes to the corner, he takes a bend. He bends inward with respect to vertical by an angle theta, so that the necessary centripetal force toward the center of the imaginary circle can be provided by the component of normal reaction, that is r sin theta. It follows this angle theta what he is bending, through which the cyclist should bend, will be greater if the angle through which cyclist should bend will be greater if the radius of the curve is small. That is, the curve is sharp curve, the cyclist have to bend more. Secondly, the velocity. Velocity of the cyclist is large. If velocity is very large, he has to bend a greater angle because he has to provide the necessary centripetal force. For a sharp turn with a high speed, if the cyclist comes and want to negotiate a curve, he has to bend angle theta more because theta is tan inverse V square by Rg. So if R of the curve is very small, sharp bend, and velocity is very large, theta bend should be much greater. So did you follow this point? Why the cyclist bends when he comes across a turn or a curve? Because he has to provide himself the necessary centripetal force, and he does so by leaning inwards on a horizontal track. If friction is there, then friction also help him to provide the necessary centripetal force, which we have already studied. Let us see illustration here to understand more clearly. A motorcyclist moving with a velocity 72 km per hour. What is the speed? 72 km per hour. In SI unit, we have to multiply by 5 by 10, so it becomes 20 meter per second. On a flat road, takes a turn on the road at a point where the radius of curvature of the road is 20 meter. Radius of curvature given to us 20 meter. The acceleration due to gravity is 10 meter per second square. In order to avoid skidding, he must not bend with respect to the vertical plane by an angle theta greater than. So to provide the necessary centripetal force, the angle theta he should bend minimum, it is equal to tan inverse of V square by Rg. Now we know the value of all the quantities. We can get tan inverse of velocity is 20, 20 into 20, 20 square, divided by radius is 20 into 10. So that is nearly tan inverse of 2. So theta he should bend should be not be greater than tan inverse 2. So the option tan inverse 2, the option B is the correct option. So if he bends by theta equal to tan inverse 2, he can provide himself the necessary centripetal force for negotiating the curve comfortably.